Okay, welcome to lecture here. We're going to get started on chapter 5, I think. Again, the notes should be up online if you need them. Let's see, something to write with would be good. There we go. Okay, a couple of things. We finished up chapter 4 last time. There is a section of chapter 4 which deals with molecular orbital theory, and we're not going to actually cover molecular orbital theory, so you don't have to worry about that part of chapter 4. So again, from chapter 4, basically you got the geometry, you got the hybridization, you have the polarity, and I think that will do it for chapter 4. So again, there is a part of chapter 4 which deals with what's known as molecular orbital theory, and we're going to kind of skip it because you know who likes that really. So we're going to skip that part of it, I think. All right, so that should bring us to chapter 5. And chapter 5 here, we're going to talk about grams, we're talk about moles, we're going to talk about molar mass and doing those type of conversions. We'll also talk about some different types of formulas like empirical formulas and molecular formulas, and we'll talk about how to sort of calculate those and figure those guys out as well. And I think we'll get started then. So the first thing we're going to really talk about is the atomic mass of an element, and the atomic mass can be found on the periodic table. And when you look on the periodic table, it is the number that we see on the bottom, actually. And so, for example, hydrogen there is something like 1.008. And the atomic mass obviously is based on the particles that make up atoms. And in that case, as we know, we have protons, electrons, and neutrons that make up atoms and the masses of those things. Obviously, atoms are extremely small, as we talked about, so you can't just kind of pick one up and slap it down on a balance or anything like that to weigh it. So much like a lot of things in chemistry, they do have to kind of come up with sort of a standard. And they come up with sort of a standard to compare everybody else to. And in the terms of atomic mass, the standard that they chose was really an isotope of carbon. It was the carbon 12 isotope. Again, the 12 being the mass number there. And the carbon 12 isotope has exactly the mass of 12, what is referred to as 12 AMU, AMU being atomic mass unit. And that's usually what we can actually pull off of the periodic table. We can pull off the periodic table that number. And one unit that we use a little bit of in this chapter, then not so much after that, would be we could say that there's 1.008 atomic mass units in one atom of hydrogen. So that's sort of the relationship technically that you get when you pull these numbers off of the periodic table. So as I mentioned, the carbon 12 is basically the isotope that they chose to use. And they basically compared all the other atoms to it for the different elements and said, hey, this guy is only like 1% as massive as, say, the carbon 12 isotope. This guy is like 20% as massive of the carbon 12 isotope. And that's essentially how they came up with all those atomic masses that we see up there on the periodic table. And so by doing that, for example, we could do a very simple calculation to sort of figure that out. So for example, experiments have showed that if you take like a hydrogen atom, it's only about 8.4 as big or massive as a carbon 12 isotope. And that's basically what this little calculation is right here. If we take 8.4% and convert it into a decimal, so 2 places to the left there, gives us 0.084 times 12, which is the atomic mass of carbon 12, gives us 1.008. And again, that is the number that you see on the periodic table underneath something like hydrogen. They did similar calculations for things like oxygen, which is 16, iron, which is 55, 85. And again, you can find the atomic masses listed up there on the periodic table. Now, you may wonder when you look at something like carbon on the periodic table, it actually says 12.01 for the atomic mass that we see for something like carbon. And you may say to yourself, if carbon 12 is sort of the isotope that they used to sort of figure out the atomic mass, how come it's not 12 even on the nose for the atomic mass? Why is it 12.01? And the reason is because the numbers that we actually do see on the periodic table, although most people really don't sort of call it that, they're actually average atomic masses. And they're average atomic masses of all the naturally occurring isotopes for that particular element. So for example, carbon, there's carbon 12 isotope, and there's also the carbon 13 isotope. And what we actually see up there on the periodic table is basically the average value you get when you take both of those isotopes together. So and that's the number that we get. So to actually calculate the atomic mass for a particular isotope, there is sort of a simple sort of formula that you do. The atomic mass is equal to the percent abundance, is sometimes referred to, times the atomic mass of the first isotope, plus the percentage abundance of the next isotope, times the atomic mass of the next isotope, the second one. And if you had more, you just kind of continue that sort of pattern. You take the percentage, convert it into a decimal, times the atomic mass of each isotope, and you add them together. And that's important. Sometimes people always want to multiply this part here, but we're adding each of those guys together when you do that. So although there are naturally occurring isotopes, they do occur sort of in a different percentage. So for example, the carbon 12 isotope maybe occurs like 98% of the time and 99% of the time. And the carbon 13 isotope maybe occurs about 1% of the time. So we use those percentages and the atomic mass of each of those basically to calculate the atomic mass of a particular element. So if we look at something like carbon, here are those numbers here. So for example, the natural abundance or relative abundance is sometimes referred to of carbon 12 and carbon 13 is, like I said, about 99% carbon 12 occurs, this isotope, and about 1% of the time it's the carbon 13 isotope. So we can determine basically the atomic mass by doing that calculation, and that is what we see here. So we're going to take the percentage of the first isotope, which is 98.89%, convert it into a decimal. So again, you can either move the decimal place 2 places to the left, you could divide it by 100, whatever you want to do there. We're going to multiply it by the atomic mass of the first isotope, the carbon 12 isotope. Then we're going to add it to the percentage of the second isotope, which again is 1.11%. Again, divided by 100 or move the decimal point. We're going to times that guy by the molar mass of the carbon 13 isotope. And if we do all that math there, we end up with a number of 12.01, which again, if you look on the periodic table, that is exactly the sort of the number that you typically will see underneath carbon. So what we are actually seeing on the periodic table is the average atomic mass of each of those elements, and they're the average atomic mass of all the naturally occurring isotopes for that particular element. And when we typically do the atomic mass off the periodic table or use that number, usually 4 significant figures is sort of what we go with. It is important to remember that if you could actually sort of pick out a carbon atom, you would really never find one that has an atomic mass of 12.01. You'll find one that has either an atomic mass of the carbon 12 isotope, which is 12, or you'll find one that has the atomic mass of the carbon 13 isotope, which is our 13.00335 number there. Again, you'll never really find one that has a mass of 12.01, but again, that is sort of the average atomic mass and what we sort of consider the atomic mass of carbon. Questions on that there? So again, that formula here, we had just 2 isotopes. It did add up to 100, which is a good thing to sort of think about. Here we have 98.9% basically and 1%. So just roughly looking at these percentages, we do add up to about 100%. And you do want to make sure of that when you're doing these type of problems. Again, if you don't add up to 100%, then you're missing an isotope somewhere along the way. So that's usually a good thing to think about. Any questions on that particular one there? Okay. Now, atoms have very tiny masses. So again, we sometimes will create some numbers to help us get a little bit bigger of numbers. So this is sort of the relationship here between an AMU and grams. 1 AMU is 1.66 times 10 to the minus 24 grams. And because of this conversion and really everything that's happens, what ends up happening is, and how we usually use these numbers, as we will see a little bit later on in this chapter, is, for example, in grams per mole. So the molar mass, which is grams per mole, is numerically equal to the atomic mass in AMU per atom. And that's sort of the conversion there that gets you there. Is basically Avogadro's number, makes it almost the same value that we see. All right. So again, we could do some calculations in AMU here. So if we had 431 atoms of carbon from the periodic table, again, we could get this relationship that there's 12.01 AMU in a carbon atom. Really gives us 2 conversion factors, 12.01 AMU per atom. R an atom is 12.01 AMU. And here we would just do a sort of dimensional analysis way. Atoms cancel. 431 times 12 gives us our 51.76 AMU as the atomic mass of 431 carbon atoms in this particular case. So we could use this sort of like we would normally use molar mass, and probably outside of this chapter won't be using AMU all that much. Most people don't use that very much. We use grams per mole, as we'll talk about a little bit later on in this chapter. Here's just another one. Again, we could get this relationship from the periodic table. And again, it is the number that we see underneath it, 2698 for our aluminum. And again, that means that there are 2698 AMU in an aluminum atom. And that is how we get it there. Again, atoms canceling, giving us 2024 AMU for our aluminum. So how do we figure out things like the percent abundance or sort of the masses of these different isotopes? We could use a process which is sometimes referred to as mass spec. And basically what it's able to do is really separate out isotopes based on their mass. So it kind of goes down a tube, it gets bended through sort of electrical field and magnetic field. And basically what ends up happening is it comes out as basically fragments. And it comes out as fragments on sort of the detector. And those different fragments are basically different isotopes of a particular element. And they could do some calculations basically to figure out the percentage of each of those that there are basically naturally occurring. And that's how we sort of get those values of this guy occurs, 12% of the time, and it has sort of this mass, this isotope, or, this one's 98% of the time, and sort of this mass that goes with it. And what we typically get is a mass spec type diagram that comes out. And as you can see, this is for chlorine. And we do get some separation of the chlorine 35 isotope from the chlorine 37 isotope. They also gives us some different sort of peaks that occur, roughly 75%, 25%, that's about 100% total, and are naturally occurring isotopes. And again, we would have the mass that comes out here. And that's how we really do get sort of those values that we could use to sort of calculate things like atomic mass for a particular element. Here's a much prettier picture of really what's going on. So really your sample comes in here, it gets heated up as it goes through here, again, gets sort of separated by an electrical field and then a magnetic field as it sort of bends, and then it gets separated by sort of mass. And on the left here, as you can see, lightest guy is sort of coming out, heavier guy is coming out a little bit further down on sort of the detector, and again, giving you some peaks that you typically would see in that sort of graph that we just saw. So why don't you try one here? If copper is 69.17%, copper 63, with a mass of 62.9396, and the rest is copper 65. Find copper's atomic mass in AMU. So take a couple of minutes, see what you come up with here.
Professor Efron, I had a question about percent abundance. Are we able to determine percent abundance, or are those things usually given to us?
Are you asking, you kind of cut out, but are you asking like, would you have to determine that perhaps, or is that usually given to you?
Yeah.
Is that what the question is? It can be either way. So the idea is like in this particular one, for example, right? If you had all of the naturally occurring isotopes, you would have 100% of something. So sometimes you could use that as your way to figure out maybe a missing percent abundance and stuff like that. So sometimes they give you all of it. Sometimes they may give you one that's missing, like in this particular problem here.
We're still using sig figs here, right? So would we go to 4 here?
Yeah, you could go to a 4 sig figs probably on the percentage, looks like, perhaps. Or a couple of decimal places should be fine. Okay, so let's take a look here and see. So what's given to us is we have one isotope of copper, which is 63, and it has a percentage of 69.17% that it occurs. It has an atomic mass, that particular isotope, of 62.9396 AMU. We also have a copper 65 isotope, Doesn't give us the percentage, but does give us that it is 64.9278 AMU. And we're looking for the AMU, or the atomic mass of copper. So we do want to basically figure out the percentage that's missing here. So as I was saying just a minute ago, if this is all the sort of the naturally occurring isotopes, you could assume that if you had them all, that would be 100%. And since we have 69.17% given to us already, if we subtract those two, that will give us the missing percent that we got going on. So 100 minus 69.17 gives us 30.83%. Should be the percentage of our carbon-65 isotope. Again, adding those together should give us the 100% of all the isotopes. So again, this is a way, if you're not sort of given all the percentages, you could usually assume 100% and find sort of the missing percentage that you have. At this point, we have pretty much everything that we need to calculate the atomic mass there. So the atomic mass would be, again, the percentage of our first isotope, which is 69%, converted into a decimal, so 0.6917, or take the 69.17 and divide it by 100. We're going to times it by the molar mass of that first isotope, which would be this. Again, we're going to add this to our second isotope, converted into a decimal, 0.3083, times the molar mass, or atomic mass of our second isotope. And if we do all that good stuff there, and your calculator doesn't die again. Let's see here. Should really find me a battery on this thing. Let's see. 62.9396. There we go. Plus 0.3083 times 649278. So we do end up with something like 63.55 AMU. And there was a sort of a question on sort of sig figs. So technically speaking here, when we did that part of the calculation, we ended up with 43.535, and technically here we should end up with 4 sig figs, which would have been something like this. And over here, when we did that side of it, if you want to get really technical here, we should also have ended up with 4 significant figures, which would have been 20.17. Now, when we added it together, because the last thing we would have done was adding, we would look at decimal places. So that's why I said we should probably go to 2 decimal places here, as that would be sort of the final step that you did there. And again, I didn't really do too much rounding, so hopefully get pretty close to the same one. If you did it sort of that way, really stringently there, you get 6371. But if you didn't round to the very end, that's technically where you should end up, is at 2 decimal places. Question on that, again, if you go to the periodic table and look under copper, you do see that number there, which is good, I guess. Yes. Any questions on that particular one? All right, why don't we try one more here just to make sure. Let's say we had 3 isotopes of magnesium, and magnesium has a molar atomic mass of 24.31 AMU. Let's see, if we have magnesium 24 with an atomic mass of 23.99 AMU and a percentage of 78.99%, and magnesium 25 with a mass of 24.99 AMU and a percentage of 10%. What is the atomic mass of magnesium 26? in AMU. So give that a go, see what you come up with. I'll do it too since I just made it up-ish. Hopefully end up at the same place.
Is it 25.99%?
It's a good question. I think so. I hope so. Let me see. So let's take a look and see if that is right or not. So in this case, we do have 3 isotopes given to us. And at this point, we want to actually figure out the mass of the individual isotope that's here. So again, in this case, the atomic mass will equal the percentage of our magnesium 24 times the AMU for magnesium 24 plus the percentage of our magnesium 25 times its AMU plus the percentage of our magnesium 26 times its AMU. So we do have this one, we have everything here, we have everything here. We really don't have this guy. We can find the missing percentage. So the percentage of magnesium 26 will be 100% minus our first isotope, which was 78.99%, minus our second isotope, which was 10%. So doing all that, we know now that the magnesium 26 isotope is 11.01%. So if we put in our numbers, we know that the overall atomic mass is 2431. Our first isotope, again, converting our percentage into a decimal and timesing it by the atomic mass of that first isotope. Again, adding it to our second isotope, also converted the percentage into a decimal times the atomic mass of our second isotope plus, I'll just go here, our third isotope that we now know is 0.1101 times, I'll just call it X at this point. That's kind of what we're looking for at this point. So what we could do is kind of clean up both of these guys. So if I clean up those guys there, I get 0.7899 times 2399 plus 0.1 times 2499 gives me 2431 AMU equals 2145 AMU plus my last isotope over here, basically. So we're going to subtract this to the other side. And when we do that, 24.31 minus 21.45 gives us something like 2.86 AMU equals our percentage. And again, I'll just call it X, what we're looking for. We'll divide that to the other side. And that gives us our missing isotope being 2598, give or take, AMU. Any questions on that calculation right there? Okay. So again, this is essentially how you can calculate the atomic mass of an element, basically how they're all calculated there on the periodic table. And as you can see in this example, you know, you could even find the mass of, say, one individual isotope if you know enough information. Any questions on that part? Okay. So then let's talk about some important sort of numbers in chemistry that we deal a lot with. And in life, we have a lot of names of things that represent a certain amount. So if we say we have a dozen, right? You could show up with some dozen roses. That means 12 roses, I suppose. Show up with 12 eggs, I suppose, is also a dozen. You might get a different response, I suppose, depending on which one you show up with. If you have a pair of something, that's 2. Heck, if you're old enough, maybe you remember gross they used to use for like pencils. It's 144. So in chemistry, we do have a name of something that represents a certain amount of an object, and that is the mole. And the mole, abbreviated MOL, they had to abbreviate it somehow, so they killed the E at the end there. And important to remember, though, that when you do see MOL, it does represent the abbreviation for moles and not molecules. So that's very common. People kind of mess that up. They see that and automatically think sort of molecules. And the mole is basically the amount of substances there are in exactly 12 grams of our carbon-12 isotope. And it actually does have sort of a numerical value, and that's what's known as Avogadro's number. And we usually round it to right about there, 6.022 times 10 to the 23. So 1 mole of anything equals 6.022 times 10 to the 23. And in terms of the units here, the units really can be anything. A lot of times in chemistry, we do atoms. We sometimes do molecules with it. It could be something like particles. It could be something like shoes, pizzas, whatever it may be. Probably going to use atoms and molecules, maybe a little bit more in pizzas here, but those are the common sort of units that we commonly do use with this. And really, Avogadro's number is our conversion factor to go from moles to atoms or molecules, or backwards going from atoms or molecules back to moles. So it is sort of our conversion factor. We could use it like a conversion factor, which means we can use it with the Avogadro's number up on top. Atoms or molecules per mole. Or we could flip it around and put the mole up on top and use Avogadro's number pretty much on the bottom. And we essentially can pull Avogadro's number for anybody on the periodic table. So if I had 1 mole of hydrogen, it would have 6.022 times 10 to the 23 atoms of hydrogen. If I had 1 mole of iron, it would have 6.022 times 10 to the 23 atoms of iron. You could even do it for things that are not atoms, but things that are molecules as well. So if I had 1 mole of water, I would have 6.022 times 10 to the 23. The units here would be molecules of water. If I had 1 mole of methane, that would give me 6.022 times 10 to the 23 molecules of methane as I write through the shoes there. And you could use it for any of those sort of applications. And again, it really is sort of our conversion factor to do that conversion. Another really important sort of conversion factor is molar mass. And molar mass is how many grams there are per mole of a substance. And that does come from the periodic table, where we were just looking at that atomic mass. So when we use the bottom number on the periodic table, that is how many grams there are per mole. So there would be 1.008 grams per every mole of hydrogen. And the molar mass would be considered 1.008 grams per mole. We could do it from anybody on the periodic table. Again, if we look at iron and the number underneath it, 5585, that means that there are 55.85 grams of iron in every mole of iron. We could also do it for things that are molecules by adding up all the parts. So there are 2 hydrogens, each at 1.008 grams per mole, plus 1 oxygen from the periodic table, which is 16 grams per mole, gives us a molar mass of water of 18.02 grams per mole. So when we're calculating the molar mass of something, it is based off of the formula. You basically add up all the parts, and we do take that bottom number from the periodic table as the molar mass, which is grams per mole. And it is numerically equal to the atomic mass that we were just talking about. So that sort of conversion where you go from atoms, AMU to atoms to grams per mole, it basically ends up being the same number. And we use molar mass really as our conversion factor to go from grams to moles, or if you need to, moles to grams. So it is, again, a conversion factor that we get from the periodic table. And even though we say hydrogen is 1.008 grams per mole, and that is the molar mass, we can use it like a conversion factor and flip it around and sort of do dimensional analysis and use it that way as well. So Avogadro's number, our conversion to go from moles to atoms to molecules. Molar mass is our conversion to go from moles to grams, grams to moles. And we can put them all together because in 1 mole of hydrogen, there is 6.022 times 10 to the 23 atoms of hydrogen. And that means that in 1 mole, which is that many atoms, there is 1.008 grams of hydrogen as well. So they're all related to each other. Same thing with the water. You could say in 1 mole of water, there is 18.02 grams of water. And in 18.02 grams of water, there would be 6.022 times 10 to the 23 molecules of water. So they are sort of all related to each other all the way through there when you look at that. Typically speaking, like I mentioned earlier, if you pull a number off of that periodic table, you typically go 4 significant figures. So depending on the periodic table you may be looking at, there may be a lot of numbers underneath the symbol. Usually, traditionally, 4 significant figures is what we take for something like molar mass to use in a calculation, or if you're just adding up the molar mass of a substance, usually that 4 significant figures is what you go with. Any questions on that there? Here is a mole of all these different sort of substances, and it does look like perhaps different amounts of each of those. And the reason that is because when these all may be 1 mole of something, 1 mole of each of these guys does represent sort of a different amount. So if I had 1 mole of sulfur, that represents about 3207 grams. 1 mole of carbon represents about 12.01 grams, while 1 mole of copper is 6355 grams, and iron would be 55, 85 grams. So although we may be looking at 1 mole of each of these sort of substances, 1 mole does represent sort of a different amount in terms of grams when you look at, different substances there. All right. Here are some conversions and some relationships between AMU, and this is ultimately why our molar mass and atomic mass in AMU are the same. Because they're related to each other really by Avogadro's number. So when you sort of do the math, it really does come out basically the same number as you see there. And again, here's our sort of conversions that we talked about going from one to the next. So oftentimes though, people do some not the greatest things, I guess is the best way to put that. For some reason, people learn Avogadro's number and they feel like I should use it in every calculation I ever know or ever see, because why else would, Efron make me learn this number if I don't have to use it in every single calculation? So just be clear that you should not use Avogadro's number in every calculation you ever do. You should only be using Avogadro's number in any type of calculation where either you are trying to find something that's in atoms or molecules, or you're given a number that's in atoms or molecules. If there's really no mention of any of that, you really shouldn't be doing anything with Avogadro's number. Usually people will kind of divide by it at the beginning, maybe multiply by it at the end. They kind of cancel it out themselves, but try not to use it in every calculation. Just make sure that you use it in the right calculations. All right, so why don't you give it a go here. What is the number of grams of iron in 15.7 moles? In case you don't have a periodic table, iron is 5585 grams per mole. Take a minute or two here and see what you come up with. Okay, so let's take a look here and see what we've got going. All right, so we are given moles. So the first question is, should we use Avogadro's number? And the answer is no, because we are given moles. We're looking for grams, has nothing to do with Avogadro's number. So really, we want to go from moles to grams, and it is the periodic table that allows us to do that in the molar mass. So we would start with our 15.7 moles of iron. Again, we could do sort of dimensional analysis here. So we have moles on top, so we do want moles on the bottom. So the mole and 5585 grams of iron. Moles will cancel, going to leave us grams, and that's going to be 15.7 times 5585, going to give us 877 grams of iron in this particular case. 3 sig figs based off of that number, probably just more of an exact number. Don't have to worry too much about it. Any questions on that calculation there? Okay. So let's take a look at another one here. I think you have, let's see here. How many moles of lithium are there in 77.8 grams of lithium? And again, lithium from the periodic table, 6.941 grams per mole. So based off of the last one that we were looking at, the number that we started with had 3 sig figs. You probably wouldn't take the molar mass into account. Even if you did, it's 4 sig figs. So we're multiplying. So the least number of significant figures is 3. So you should end up with 3 sig figs at the end here at 877, which would be 3 sig figs. So on my calculator, when it came out, it was 876.8. So we would look at this number, which is why I rounded up in that particular case. All right, so looking at this one here, we have grams given to us. We want moles. So same idea here. Nothing mentioned about atoms, nothing mentioned about molecules. So we don't want to use Avogadro's number. Again, it's going to be going from grams to moles, which is a super common conversion. It is going to be the molar mass from our periodic table to do that. So that's going to be 77.8 grams. Again, using it so that the units cancel out, we're actually going to be dividing by the grams part, or putting the grams part on the bottom, and up on top would go a mole of lithium. Grams will cancel each other out, and we will end up here with go with a 11.2 moles of lithium. Again, in terms of sig figs, still looking at this number here, 3 sig figs and 3 sig figs on that number at the end. Question on that? It's there. So obviously, like I said, a very common calculation. You'll do a lot of those sort of calculations for sure. So why don't you give this one a go? How many atoms are there in 0.551 grams of potassium? And potassium on the periodic table, in case you don't have it, is 3910. Okay, so let's take a look at this one. So we are looking for atoms. So that is the keyword there. We are looking for atoms. So somewhere along the way, we do need to use Avogadro's number. But we are given grams. So we do need to sort of go from really grams to moles, because moles is what we need to use Avogadro's number to go to atoms. So the first step is we really need to take the grams into moles, and we could do that by using the molar mass from the periodic table. So 0.551 grams of potassium. Here we're going to divide by the molar mass, which means we're going to put the grams on the bottom from the periodic table. And if I stop the calculation right at this point, I am left in units of moles, which is close to what I want. But remember that moles is not molecules, right? It is actually moles, obviously, the MOL there. So we do need to use 6.022 times 10 to the 23 atoms equals 1 mole. So you could either get an answer at this point, or you could continue on with the calculation. I'm going to continue on with the calculation. So right now my moles are on top, so I want to get rid of them. So I'm going to put the moles of potassium on the bottom. Avogadro's number is going to go up on top. And since we're just dealing with potassium, it is going to be an atom here. Moles are going to cancel. The only unit left standing at this point is atoms. So we're basically going to multiply across the top there. So we're going to take 0.551 times Avogadro's number using our exponent button, and we're going to divide it by 3910, and we're going to hit equals. And when we do all that good stuff there, we end up with 8.49 times 10 to the 21 atoms of potassium in this particular case. Again, looking at probably both of these guys here as more like exact numbers, not really worried about the sig figs here, defaulting probably back to this number for sig figs, which is 3, and that gives us 3 significant figures right there in terms of our answer. Question on that particular one. Again, you could get an answer after the first step and then continue on with the next step. Perfectly fine. Again, I wouldn't round too much there until the end. Again, as you round a little bit here, a little bit here, you're kind of moving yourself probably farther away from the right answer and stuff like that. All right, try a couple more here just to make sure. So give these two a go. How many moles of helium and how many grams of zinc in these two? Let's see what you come up with. Okay, so let's take a look at the first one. Again, we have grams given to us. We're looking for moles, so no need to use Avogadro's number here. So it is going to be the molar mass from the periodic table. So 5.46 grams of helium using our molar mass really as a conversion factor. We're essentially dividing by our molar mass. Grams will cancel out here, and we will end up with 1.36 moles of helium in this particular case. Again, based off of that number there. And the second one here, how many grams of zinc are there in moles? So same idea. We're looking for grams for moles, so the molar mass from the periodic table. And again, we would start with our 0.256 moles of zinc, using our molar mass in this case, actually multiplying by the molar mass. Again, the moles will cancel, and that will get us something like 16.7 grams of zinc. Any questions on those two there? So just a reminder, when we do the molar mass, and whenever you're asked to calculate the molar mass, it is just based off of the formula. So again, if we had H2O, we would go to the periodic table for the 2 hydrogens and the 1 oxygen. And that is even the case if it was in a formula where it said like 4H2O was the coefficient. The coefficient has nothing to do with the molar mass. The molar mass, whenever you calculate it, should only be based on the actual formula by itself. And that's why when we say the molar mass of something is 18.02 grams per mole, it's always 1 mole, which means just one of the formulas by itself should always be how you calculate the molar mass. Sometimes when people see it in equations, they want to kind of insert that into the molar mass, and you shouldn't do that. So again, only from the formula of the molar mass from the periodic table. All right, let's see what we got going here. I think let's get that one. Let's talk a little bit about this one here, and we'll kind of look at it together. We want to know how many atoms of hydrogen, or how many hydrogen atoms are there in 72.5 grams of C3H8 and O. So we definitely know that we need to use Avogadro's number here because we do have atoms mentioned. And again, that means that 1 mole is 6.022 times 10 to the 23 atoms. The difference is here we're interested in just the hydrogen part. We are really not interested in the entire thing, which is what we're given. So when you're interested in, say, one aspect of a formula, be it the hydrogens like it is in this case, be it, say, the carbons or the oxygens, you could actually use the formula itself as a conversion factor. And when we look at these small numbers on the bottom, the subscripts, those are basically how many moles of each of those elements we have. So we could come up with several conversion factors from the actual formula itself. We could say in 1 mole of the entire thing, there is 3 moles of just carbon. And again, the 3 would come from here. We could also say in 1 mole of the entire thing, there is 8 moles of hydrogen. And again, the 8 comes from right there. It is basically the moles of it. And we could also say in 1 mole of the entire thing, there is 1 mole of oxygen, also from sort of the subscript that would normally be there. So this is going to really be our conversion factor here. That's going to allow us to go from the whole thing into just hydrogen. Now, in order to use that relationship, since it's really a mole to mole relationship here, we do need to convert the grams into moles first. So to convert the grams to moles, that is going to be the molar mass from the periodic table. So in this case, we need to add up all the parts. So we have 3 carbons at 12.01 grams per mole, plus 8 hydrogens at 1.008 grams per mole from the periodic table. plus 1 oxygen at 16 grams per mole from the periodic table. And that means if we add all that up, we get something like 6009 grams per mole, which is the molar mass of C3H8O. So we're going to use that as our conversion factor. So we're going to start with the 72.5 grams of C3H8O. We're going to use that molar mass that we just calculated to convert those grams into moles. Grams will cancel. You don't have to get a number at this point, but I'll put up a number here just in case. Here it's 60.09. We'll go with 1.2065. I'll take it to a few digits. Moles of C3H8O. So we did a nice conversion to convert it into moles, but again, we do need to now get rid of the entire thing and end up with just hydrogen. So we're going to use this as our conversion factor to do so. And if we do that, 1.2065 moles of the entire thing. And again, from the actual formula, we could use it. 1 mole of the entire thing gives us 8 moles of just hydrogen. So that is how we're going to go from the entire thing to just hydrogen. So we'll take that and times it by 8. Gets us something like 9.65219. I'll take it to a few digits. Moles of hydrogen. Any questions on that so far? Now, I'm at moles of hydrogen, which is close to what I want, but I do want atoms. So the last thing we need to do is use Avogadro's number here. And that is going to put Avogadro's number up on top. 6.022 times 10 to the 23 atoms per mole of hydrogen. Moles are going to cancel. I'm going to run out of room there, so I'm going to multiply 6.022 23, and I'll just put it right about here since I'm out of room at the bottom. We end up with 5.81 times 10 to the 24 atoms of hydrogen. So sometimes, and it very commonly occurs, that they're not necessarily interested in the entire sort of formula. They may be interested in just one element of the formula. And you could actually use the formula itself as a conversion factor where the subscripts are the moles of each of those elements. Any questions on that there? All right, so a couple more then. Let's see what we got here. All right, so why don't you give these two a go, and I'll give you some numbers to help. So carbon is 12.01 grams per mole. Hydrogen is 1.008 grams per mole, and oxygen is 16 grams per mole. All right, how many moles and molecules are there in 23.2 grams of ethanol? Okay, so we got first one, how many moles and grams? So again, we don't need to use Avogadro's number here, so we do need the molar mass of this whole entire thing. So we would go to the periodic table to do that, and we got 2 times 12.01 for our carbons, plus 6 times 1.008 for our hydrogens, and a 16 for our oxygen there. And that looks like 4607 is the molar mass there. So that's 46.07 grams per mole. Again, we're going to use that as a conversion factor. That's going to give us 23.2 grams of C2H6O. Again, grams up there on top. So to make sure it cancels out correctly, we're actually going to divide by this. Put the grams on the bottom. Again, the grams will cancel here, and it looks like we end up with a number. And it looks like something like 0.504 moles of C2H6O would be our top answer there. Any questions on that one? Again, 3 sig figs off of that first number there, not so much this number. At this point, we actually continue on since it's really the same question. At the second part, though, we do need Avogadro's number because it does mention molecules. So again, 1 mole of anything is 6.022 times 10 to the 23. Here we will use molecules because C2H6O is a molecule. Continuing on with our number from the first part, we're going to multiply by Avogadro's number. So he will go up on top. Per mole on the bottom. Again, the moles will cancel, and we will end up with something like 3.03 times 10 to the 23 molecules. Any questions on any of that there? Questions on how to do grams, moles, molecules, Avogadro's number, any of that stuff there? Okay, so I think we'll skip the next example since we've kind of done some like that. The next thing we're going to talk about, though, is percent composition by mass. So we can figure out basically the percentage of each element in a compound based on the formula that's given to us and the molar mass of the compound and how many, say, carbons there are, hydrogens, whatever elements that may be present. So, for example, if we wanted to figure out the percentage of each of the elements in our C2H6O, the first thing that we would want to do is figure out the molar mass, just like we just did on the previous problem, actually. So again, that would be the 2 times the 1201 plus the 6 times the 1.008 for the hydrogen and the 16. So just like we just did in that previous problem there, the molar mass of this entire compound is 46.07 grams per mole. So we can find the percentage of each of the elements that are present by using the formula here, basically the number of moles of each of the elements times the molar mass of that element divided by the molar mass of the entire compound. So if we wanted the percentage of carbon, for example, there are 2 carbons in the formula here, basically 2 moles of carbon. So we would take 2 times the molar mass of carbon from the periodic table. We would then divide it by the molar mass of the entire compound, which is 46.07. And we would times it by 100%. And if we do all that, we will end up with something like 52.14% carbon. So this compound is made up of about 52% carbon. We could do the same calculation for our other elements, for our hydrogen. In hydrogen here, there are 6 of them present. So we would take 6 times the molar mass of hydrogen from the periodic table, divided by the molar mass of the entire compound, times 100%. And if we do that, we do end up with something like 13.13% hydrogen. And our last one here would be the percentage of oxygen. And again, in oxygen, there's actually just 1 oxygen present. So basically 1 times 16 grams per mole divided by our 46.07 grams per mole times 100% tells us that it is about 34.73% oxygen in this case. Now, there's a couple of things you could have done a little bit differently in terms of figuring out, say, the last one. Because I already figured out my carbon and hydrogen at that point, oxygen is the only other element there, so you technically could have went 100% minus the 52.14 minus the 13.13 should end you with that number as well. So again, that's another way you could have got that last element by assuming 100% and sort of subtracting from 100 the percentages as well. What this tells us is based on mass, most of the mass here is carbon and oxygen, making up about 86% or so of this particular compound, with hydrogen being the least percentage by mass in this particular compound. So to figure out the percent composition of each element in a particular formula, basically get the molar mass of the entire thing, take the mass of each of the individual elements that are present there, and divide it by the mass of the entire guy, times it by 100%. Again, should add up to about 100%. You know, give or take rounding, you should be in that ballpark in terms of percent composition. Any questions on that there? Okay, I think it's probably a good place to stop. I think so. And so we will stop there for lecture. Any questions on any of that stuff? Okay, make sure you type here, and then we'll decide what happens in the lab when we get there in like 15 minutes or so. So I'll see everybody about 15 minutes, 7:15, and we'll talk about lab and all that good stuff. All right, see everybody in a bit.